If you ask a standard physicist about the golden ratio, roughly 1.618, you will likely get a dismissive answer. They will tell you it is an aesthetic coincidence or a neat numerical artifact restricted to macroscopic biology. These recursive geometric patterns, known as phyllotaxis, demonstrate a literal scaling law that governs complex organic growth. Phyllotaxis is the arrangement of leaves, seeds, or scales on a plant stem, and its presence in biology is well documented. Hard quantum mechanics identifies 1.618 within fundamental phase transitions, suggesting a scaling law that extends far beneath the macroscopic world. Consider a 2010 paper published in the journal Science. Researchers were examining the quantum critical point of a cobalt niobate Ising chain. An Ising chain is a one-dimensional model of magnetic spins, and a quantum critical point is the exact condition where a system undergoes a phase transition at absolute zero. In this state, the system revealed a hidden E8 symmetry. This plot maps the phase transition. When the system shifts, the ratio of its lowest resonant frequencies is exactly 1.618. In Hardy's paradox, the maximum probability of non-local quantum correlation peaks at exactly phi to the negative fifth power, or 0.09017. Under the framework of the observer-dependent theory of everything, or ODTOE, these occurrences are mathematical requirements. Phi is the mandatory structural invariant of any discrete, iterative dynamic of self-reference. To understand quantum fractality, we must derive phi from absolute first principles. If physical reality is composed of a system observing itself, we need to locate the mathematical mechanism where a value is defined entirely through itself. We start with the simplest self-referential equation, x equals 1 plus 1 over x. We map this architecture directly to the ODTOE observation process. 1 represents the minimal basis of existence. 1 over x is the inverse action of self-observation, generating recursion. To understand how this behaves dynamically, we apply the Banach fixed-point theorem. This theorem guarantees that certain iterative, self-feeding mathematical mappings will eventually lock into a single, unchanging value. On the interval between 1.5 and 2, this mapping acts as a contraction with a 4/9 Lipschitz constant. Graphing this step-by-step sequence, starting at 1, the equation outputs 2. Feeding 2 back in outputs 1.5, then roughly 1.66. The outputs compress inward. This contraction guarantees exactly one positive fixed point. That point is exactly phi, or 1 plus the square root of 5 divided by 2. This algebraic fixed point models the core ODTOE mapping. The physical state defines the observer, and that observer in turn reprojecting the state. Phi is the gravitational center that any self-referential, iterative process will eventually fall into. Physical reality relies on both continuous and discrete dynamics. To function, it requires two distinct structural invariants. We compare these dynamics. On the left, pi governs continuous phase loops. Its transcendental nature ensures these trajectories never perfectly close, preventing an exhaustible reality. On the right, algebraic phi governs discrete recursive orbital jumps, guaranteeing maximum stability around the fixed central state. To understand why this specific number provides stability, we look to the KAM, or Kolmogorov-Arnold-Moser theorem. The core rule of the KAM theorem dictates that invariant tori and dynamic systems that possess the most irrational ratio of frequencies are the most resistant to destruction from small perturbations.
Mathematically, phi is the most irrational number in existence. Its continued fraction is composed entirely of ones. This results in the absolute slowest convergence of rational approximations. We can map this property back to recursion. If we represent the recursive Fibonacci sequence as an operator matrix, its dominant discrete eigenvalue, stretching mathematical space, is strictly phi. While pi forces the universe's continuous dynamics to remain open and infinite, phi serves as the rigid algebraic skeleton that prevents the discrete steps from shattering. We scale this discrete, highly stable dynamic up to the structural architecture of the universe, moving from subatomic quarks to atoms to complex molecules. This relies on recursive self-similarity, or infinity embedding. The exact same triadic architecture, an observer, an operator, and an observable, is nested identically inside every physical scale. Because this structural recursion between scales is an iterative mapping, the entanglement connecting these scales must inherit phi as its scaling factor. Visualizing fractal entanglement, we start at a central observer's level, D0, tracing connections into deeper recursive layers. The von Neumann entropy equation governs the structure, showing informational entanglement decaying exponentially at each deeper step away from the central node. Translating the math into physical limits gives us a strict boundary. For every structural step away from the observer's specific scale, the informational entanglement drops by a factor of exactly 1.618. This precise exponential decay is a known property of classic fractal dimensions. As you move between scales, information predictably leaks out of the system. This strict phi scaling dictates the limits of our physical reality. Observers are mathematically isolated to their own scale, only able to access a finite number of recursive layers before the entanglement vanishes entirely. Equipped with the exact math of infinity embedding, we can return to the physical anomalies. First, we look back at the cobalt-niobate Feising chain phase transition from the science paper. A quantum critical point is the precise moment of maximum systemic reconfiguration. It is the exact threshold where standard structural rules break down. In this specific moment of breakdown, the everyday noise of the system falls away, laying bare the system's underlying discrete mathematical eigenvalue, phi. Next, we revisit Hardy's paradox and its limit for non-local quantum correlation. Measuring two entangled subsystems mathematically maps an observation across the infinity-embedding recursive architecture. Hardy's probability fraction represents the strict boundary imposed by the exponential decay of von Neumann entropy. The fifth power represents the absolute depth limit of that structural connection. Finally, we scale back up to the macroscopic world to look at the patterns of the sunflower and the pineapple. Living organisms operate as coherent clusters of physical observers. Their macroscopic biological morphogenesis is forced to obey the exact same iterative, subatomic recursive scaling. The golden ratio is the algebraic skeleton of recursive self-similarity. In any system, from the topology of quantum fractals to atomic loops, phi is the mathematical fixed point that allows the universe to stably observe its own infinite complexity.